So we start from something called fluctuation theorems. They are essentially ways of characterizing open systems. They are a more recent tool. Like if you actually looked at equilibrium thermodynamics, came about like 300 years ago, right? Non-equilibrium thermodynamics is only 30 years old. So it's a very recent area, and it's gone through a revolution. It's like a silent revolution. We all hear about the deep learning revolution. Non-equilibrium thermodynamics has gone through a silent revolution inside. So it tells you to characterize any system, how to do it. And there are ways to show that if a system satisfies very specific thermodynamic conditions, right, it's equivalent to a system implementing a learning algorithm. There are no ways to distinguish between the two.
So that's the hierarchical nature of it. Similarly, if it's above the first layer, it can feed back.
Okay.
So that's this arrow. So this one comes out and branches. Too many lines, I didn't want to confuse it.
Okay.
So this green guy is really that green guy.
Okay.
This brown guy only has bottom-up input and feed-forward action.
So we can update the weight by just a Hebbian updates between tier view and the residual. This is the Hebbian update. So we can just add this residual layer on top of the Rosel's original model and do the Hebbian plastic connection between those two layers to do, dictionary updates.
How is that residual R defined here?
So R here is the residual. The residual here is the difference between the input I with the reconstruction T times phi times T of U. This is reconstruction. So this is residual. So we're just adding this layer. We can allow to do dictionary learning.
One, can we learn object representations from a stream of continuous unlabeled data? That stream, the class distribution may be changing periodically within that stream to kind of continual learning. Two, given those learned representations in a small amount of labeled data, can we perform classification onto new images? So I've tried to represent that here. Here I have just a stream of unlabeled data, MNIST images. At a certain point here, we change it up and start adding 2s and 3s into the distribution. And then the way we're evaluating our models is we're freezing at a certain point, and we're saying, hey,
this is like representations.
Yes, and we're saying, hey, you've seen 0s and 1s. You didn't know you saw them, but you've seen them. Here's some actual examples. This is a 0, this is a 1. Now, can you tell me what these images are?
This is our Dragonfly. So the Dragonfly is an interesting structure where it has groups of switches tied together to form a local connectivity, and then those local groups get glued together across a higher level of global links. So you end up with sort of a two-level structure in this setup. And so now we're just going to look at the neuromorphic workload itself running. This is in a SlimFly. The topology doesn't matter because we're going to zoom in on one node.
What about the memory? Is it completely on chip, or is it capable of accessing off chip memory? Network size gets bigger.
Yeah, also very good question. There is on chip memory, but this is very little. Yeah. So for the next generation, we will have access to memory that is in the FPGAs, but this again will be then on a slower time scale. Yeah. So the further you go out of the chip, the slower you somehow get. Yeah.
We're funneling data through Ethernet, and that's going into the Zinc, and the Zinc's decoding it and actually sending a spike packet down through the hardwired interface into the chip, right? So this basically is a north, south, east, west connection to allow you to make a tile or extension of these chips, right?
Gotcha.
And one of them for this application. Right. Yep. Yeah. So you could also funnel data in through USB. And this is basically a demonstration board, so you can build some demo app or something, right? A real-time application would probably, utilize more of these native connectors through an FPGA or some other high-speed processor.
Okay, like an external development kit or something like that.
Exactly. Yep.
This is a picture of a core in Dana 2, which is composed of a single neuron and 24 synapses that you can turn on or off, and then the cores can connect to each other, and the cores are connected to each other in a kind of nearest neighbor way, but since you got 24 synapses to work with in each of these, it gives you a huge amount of flexibility so that you can build networks that almost look like this, but with these guys tiled.
Okay, so each one of these would have been a core.
Right, exactly. Okay. And so you'll have fewer of them.
A network of networks.
Right.
So it's completely different from the way you would do classification with deep learning, standard computing, but it's kind of a cute example of how you can create that algorithmic structure with qubits to get something that's quite effective in terms of quality. So you can just you can play around with trying out different classifiers and testing it to see what the accuracy is. So I can tell you anyway that the 4 is going to be the best one, but if you want to pretend that it's random, you can try any of them. But you can try classifier 4 where they've done this custom kernel.
I believe it was used. There's a little robot, Kate. It's a really minimal walking robot, but I believe it drove Kate, or taught Kate to walk, and Kate did learn to walk and did manage to walk 1,800 steps until the battery ran out.
Always some limitation.
So I'm not real worried about robots doing anything bad. You just gotta wait till the battery runs out.
That's the nice.
I came up with sort of a hybrid model in which you use a sort of like conventional processor, which you then model as a Turing machine, and a neuromorphic co-processor, which you model as a Turing transducer. So here's the Turing machine. It has just an input. It's just a regular Turing machine with an input tape, with the restriction that it has a limited working memory in order to make sure that sort of the problem that you're going to solve is not going to be trivial.
So in this case, we think for the navigation task, it's not a good performance. So that's how the.
Be 0% of hitting, right?
Yes, that's
sort of in this.
Exactly.
Right.
That's what we got from after using the convolution neural network. It tells it's not like exactly the vertical line, but because the thickness of the line. So it's around like when the possibility of a hit is 1, the x is around like 0.1 or 0.01, something like that. But it's much better than the regular energy method. So that's something what I have done.
So with Nengo, it's a Python API, and you can code your model once, and then with one line of code, you can say which hardware device you want to run that model on. So for example, by default, your model would run on your CPU, and then if you change one line of code, you can run it on a GPU, or you can run it on Luihi, or the Braindrop chip that Kwabena talked about yesterday. So pretty much any major neuromorphic chip that's out there, Nengo has a backend that supports that chip, so you can run your model on it. So the overall philosophy is like code your model once, run it anywhere, and that's what Nengo allows you to do. So it's very flexible and compatible with a wide range of hardware devices.
So is your sound source, is the source changing based on each different respect or?
Yeah, for example, this is a sound source, the speaker. Speaker just try to replay the sound, right? Like a digit 1, 2, 3, 4, and female and male and different accent or whatever. And you speak, there's 2 variables. One is a speaker just face to the robot. The robot's ears moving, this guy. And I don't change here, but I use 0 degree. I align that with the sound source, align with here, we call it 0 degree. And then there's another variables, which is 30 degree.
So the first thing that I did at my summer internship was I worked on extending this algorithm, because originally I only worked with 2-dimensional and 1-dimensional graphs. So either the particle can go left or right, or it can go 4 directions, so up, down, left, right. And I worked on this probability tree that can extend it to any number of directions, just by stochastically spiking throughout this figure. This kind of shows which nodes in here need to spike in order for each direction to occur. So I know like 8 directions, you can't really think about that like physically, but a lot of, so a lot of what I do is on arbitrary network graphs, so
So multi-dimensional problems.
So right now we are only working with dense networks. So dense networks of about 4 to 5 layers. It works pretty well with this case. If you go a little bit higher, then we see problems basically a lack of conversions at the end with those networks, but right now with 4 to 5 networks, layer depth and it works with it.
And you say dense, so you think sparse will be easier?
I mean dense in fully connected networks.
And to gain the momentum, and finally it can break the trap and reach the destination, right? And the goal of this game is to teach the car the effective strategy of breaking the trap, right?
So the measurement signal, would that be like an observational signal?
Yeah, exactly. Yeah. So the idea of the measurement signal is the DC Hamiltonian sets up like the interaction between various qubits. Then the qubit excitation prepares like that trial. So the DC Hamiltonian is generally slowly varying. And then the qubit excitation will prepare like a run, like a trial. Then the measurement signal is sort of continuously impinging on the quantum system as it evolves in time. You're trying to probe at sort of the weak measurement limit here, so that you're picking off just a few of these microwave photons that are giving you some amount of information about the quantum system.
The way I'm consolidating is I'm not teaching these all, see, because you don't have this problem necessarily. If your regularizer term is keeping these from stepping on each other in the latent space, you could train a joint one that actually tries to have as its target mapping to the same place in the latent space. So you could train encoders rather than decoders. The only problem is, unless you've stored stuff, you're gonna end up using the generative part and then feeding it back through, right? And then you're going to have your latent vectors as your target.
Where we're going is, as the expert, she's going to teach you once or twice in the classroom. Okay? She will bring all the tools in a classroom now in 3D. I'll show you. See that's actually a tool. All these tools can now be brought inside the classroom and you can teach. Before, up until now, an expensive $100 million tool like that, you have to go inside the factory, rounding up, and then you have to train. No longer. What we're saying is all of that can now be done in the classroom.